We are Project MANAS, the official AI and robotics team of Manipal Institute of Technology. We present to you the Flight Readiness Review of Seraphim, our unmanned aerial system designed to perform the mission demonstration for SUAS 2022. Seraphim is a hexacopter which spans 6 feet wide and 2.2 feet tall. The airframe structure is primarily composed of carbon fiber, which is manufactured using the hand layer process. In-house manufacturing of ancillary mounts was done to achieve the required results. This allowed us to construct a lightweight yet rigid chassis, achieving a factor of safety of 4.2. Powered by 6 170 kV motors, coupled with 22.4-inch carbon polymer propellers, Seraphim generates a total lift capacity of 111 pounds, which translates to a thrust-to-weight ratio of 2.2:1. We used two 6S lithium polymer batteries in series to supply a total of 44.4 volts to the motors. A 3S battery is used to power all the sensors and communication electronics. We expect a total flight time of 25 minutes with the current system. Seraphim's airdrop system consists of a winch mechanism that reels down a nylon cord connected to the UGV. To navigate the UGV, we have implemented a proportional derivative controller powered by a two-wheel forward-driven differential to travel at an average of 4.47 miles per hour. Seraphim's autonomous systems are handled by a Pixhawk Cube Orange, which runs the PX4 autopilot firmware and employs a RFT900X telemetry radio to communicate with the ground station. The navigation software running on the ground station is an end-to-end automated system. On being launched, it fetches the mission file, creates a map of the region, which is then used for path planners to generate a mission, and then uploads the mission onto Seraphim. Once this process is complete, it waits for a command to be entered, receiving which, it autonomously arms the drone and initiates the mission. We use Q ground control for constant flight system monitoring and visualization of the drone's position. For this year, we have implemented the Theta Star algorithm for path planning. The paths obtained are short and reduce abrupt heading changes in the drone while minimizing the number of waypoints required. Static obstacles and flight boundaries are also buffered by a safety margin. We use a coverage planning algorithm to plan paths autonomously for ODCL, which maintain a balance between maximum surveillance area while ensuring a minimal path length. Our software automatically allows different cruise velocities for waypoint navigation and coverage regions to optimize the performance of the flight based on the task being attempted. Our imaging system uses a soft-mounted Canon EOS M50 camera. We use a Raspberry Pi 4 to transfer the geotagged images to the ground station, where it is received via the antenna tracker. An Android phone is mounted on the drone as a secondary imaging system to ensure redundancy. The images received by the antenna tracker are stored locally, where we process the images both autonomously and manually to attempt the ODCL task. The autonomous pipeline runs on each image, identifying and classifying the shapes and letters, and making submissions to the interop server. Our pipeline uses a lightweight image processing and deep learning model that works well with small datasets and minimizes false positives. For the manual approach, we use a GUI to browse through the images looking for the objects. When found, the specific area is cropped and the characteristics can be filled in using the drop-down menus. After performing and analyzing the results from 10 full mission tests, the team has decided to conduct the mission demonstration in full autonomy by attempting waypoint navigation, airdrop, and object detection, classification and localization, while continuously doing obstacle avoidance. While developing the framework of Seraphim, static, structural, and dynamic analysis simulations were performed on the CAD designs to ascertain the strength of the UAV. The motors were tested with 20 and 22-inch propellers to determine an optimum flying efficiency, ensuring maximum flight time with the given configuration of power systems. Essential components like the GPS module, the flight controller, and the radio modules were first tested on a subscale hexarotor UAV for stress testing multiple segments of our software. To reduce the impact of vibrations on Seraphim, 3D printed compliant arm mounts were implemented over rigid aluminum mounts. Wiring of all components was done to separate high current power wires and low voltage high frequency signal connections to reduce EMI interference. Multiple flights were performed in Seraphim to calibrate the PID controllers and optimize the pitch, roll and yaw rates as well as flight speeds for maximum efficiency and ease of maneuverability. To test our autonomous capabilities, we performed end-to-end tests of different modules, including software-in-the-loop simulations, to test our software architecture. With this stack, we performed 34 autonomous missions on Seraphim to ensure reliable flights. Safety features such as return to home were tested by simulating a loss of telemetry. Seraphim's waypoint accuracy was tested over 547 waypoints across 34 autonomous flights and had a maximum deviation of 5.1 feet. 96% of the tested waypoints achieved less than 2 feet deviation from the GPS location provided. Obstacle avoidance was simulated over 800 obstacles. After analyzing the simulations, 286 obstacles were avoided by Seraphim with 100% accuracy. The camera of choice provides a resolution of 6000 by 4000 pixels at 2 Hz. During the tests at an altitude of 150 feet, the overlap between successive images was around 43%. The tests also helped us estimate the range of communication and design a system that provided an efficient image capturing rate with higher geotagging precision. After having conducted multiple attempts at mapping, the team could only generate a low-quality map owing to inadequate datasets and long map generation time due to high compute requirements. Thus, the team will not be attempting the mapping task this year. Upon testing our approach on over 1300 images with various combinations of colored characters and shapes, we got an accuracy of 78% in letters, 65% in shapes, and only 14% were classified as false positives. To perform localization, GPS coordinates of each image is synchronized with the data from the flight controller, giving an average error of 15 feet for a test set of 75 distinct objects. Once we achieved a high success rate in static airdrop tests, the winch mechanism was mounted on the drone and tested in manual and autonomous flight modes. Across 23 such tests, the UGV landed at an average of 10.2 feet from the desired location and stopped at an average of 5.7 feet from the target for the drive to location task. During our manual flights, we flew Seraphim at a maximum height of 380 feet with a cruise speed of 9 miles per hour, which took around 15 minutes to complete. In our autonomous flights, Seraphim achieved a maximum height of 380 feet with a cruise speed of 21 miles per hour, averaging around a total time of 18.5 minutes. Across 5 flights, we tested against standard objects from a height of about 150 feet and achieved 78% accuracy in alphanumeric prediction, 65% accuracy in identifying shapes, 85% for shape color, and 53% for orientation of objects. Out of all the tests conducted for the UGV, it safely landed with the payload and navigated to the drive location 100% of the time. When performing full mission tests, the team scored an average of 69% on the timeline task, taking on average 12 minutes to set up, 24 minutes for mission, 7 minutes for post-processing, and 5 minutes for teardown. Seraphim averages a fully autonomous flight of 24 minutes with a waypoint accuracy of about 0.883, scoring 96% of total possible points. The UAS consistently scores 100% in waypoint navigation and obstacle avoidance across multiple tests with varying number of obstacles and maps. An average of 66% points were scored in the ODCL task, identifying 3 out of 5 characteristics usually, with a maximum deviation of 47 feet in geolocation, having 1.2 objects as actionable, and autonomy being performed on 1 out of 5 characteristics. Seraphim achieves 100% of the points in the airdrop task, ensuring the UGV lands within the minimum 5 feet landing radius and stopping well within the 10 feet of the desired location in the navigation task. After having conducted 10 full mission tests, we scored an average of 73% overall, having achieved 100% in operational excellence, and expect to score similarly in the competition. Project MANAS is confident that Seraphim is equipped with capable hardware and software to successfully complete the mission demonstration at SUAS 2022.